And so SF6 has been studied extensively as a quenching gas because it's highly electronegative. But it was due to this high electronegativity, people never used it as a low pressure gas in TPCs. They assumed that you couldn't get gas if you used it in that way. But it was interesting for us, and we decided to focus on it because it has lots of fluorine, and fluorine's the target for WIMPs. So and it's also not toxic. So we decided to look at it, and we found that you can actually get gas gain in SF6 in a low pressure TPC. We showed that you can do it with a thick gas electron multiplier or a thick gem. And then not only that, we also showed that there's this other negative ion species, SF5 minus, in addition to the primary species, SF6 minus, which you need for fiducialization and that timing to fiducialize. So SF6 is looking pretty good, and in fact, the directional dark matter community at large, because of this work that we did, has adopted SF6 as their gas to use, to consider. So that's pretty cool. And so what I started to do is I moved forward with this work, and I looked at the directionality, or the discrimination and the directionality, in a low pressure SF6 TPC. Okay, and so this is my experiment, and so this is a 60 centimeter TPC, the cathode on this side, anode on this side, and I operate this detector, or the experiments. I did lots of experiments, but the results that I'll show you are with 30 torr SF6 with a drift field. So this is the drift dimension of the detector at a 1,029 volts per centimeter. Okay, so if I open up the detector and I look at the anode plate, this is the anode plate, you see that I want to point out that there's this iron 55 source here, which is remote switchable, so we can switch it on and switch it off. And I'll show how I use this later for energy calibrations, but this is where it is. And here is the thick gem that we use to amplify our signal. And so there's some event inside the gas that drifts, and here's and the rise that the thick gem is amplified. And we read out the signal from the back surface, the positive voltage surface of the thick gem facing the anode. And so what that means is that this is a 1D readout. We're reading out the signals in 1D along the Z dimension, the drift dimension of the track. And so the signals we take, and we use a charge sensitive preamplifier to read out the charge. And then we send that signal. Our acquisition system is a digital oscilloscope, okay? And then so the, unfortunately, I don't have like a beam of WIMPs that I can send at my detector and I can study dark matter that way. That would be awesome if I had something like that, but I don't. So the next best thing is to use neutron-induced nuclear recoils and study the detector behavior with that. And so to get these neutrons that will give me these nuclear recoils, I use this DD generator, which is shown here. Okay, and I want to point out before I start showing results that there's some issues with using this DD generator, and the main issue is that it produces neutrons, but it also produces lots of gamma rays too. So these this high flux of gamma rays, they can interact in the detector, and that causes a high rate of low energy electronic recoils in our experiment, and then the nuclear recoil rate is low compared to them. So essentially, I have a neutron source that also produces a lot of electronic recoils. And so that's a big issue. It's the nuclear recoils I want to study, and I have to contend with these electronic recoils. And then compounding this issue even further is that my data acquisition system, that oscilloscope, has a 1 second dead time, which means an event occurs in the detector, it reads it out, and it takes a whole second before it's ready for another one, roughly a second. So that's a big issue, making it even harder to get nuclear recoil statistics. And so this was a big problem that I contended with for a long time, and we still have this issue. And so here's two solutions to it. One is to add lead bricks or lead shielding, seen there in the background, where you put the lead bricks between your detector on the other side and the DD generator. And so the lead bricks, the gamma rays will interact readily in the lead bricks, and they'll attenuate the gamma rays that make it to the other side by quite a lot. But unfortunately, the neutrons also will interact readily in the lead, and the neutrons will be attenuated as well. So it's sort of like it helps, but it's not quite clear. I mean, it helps a little bit, but not quite as much as we might want. The nuclear recoil rate is still low with this setup. So the other solution is to raise the trigger threshold on the oscilloscope so that we ignore all the events that are below 40 kVE. So these low energy electronic recoils, they go up to typically around like 20 kVE. So we're completely, so if, with this threshold, we're collecting a lot of nuclear recoils. And so with that, I'll describe how I select out that nuclear recoil band doing that discrimination. But assuming that I can do that, this is how I do the directionality. So what I do is I take that DD generator I just described, and I put it on the anode side, or the gem side of the detector. The gem's on the anode here. And so the neutrons flood the detector and in the positive Z dimension of the detector, and they interact and create nuclear recoils along the positive Z dimension. And since nuclear recoils have this property that this DEDX, this energy loss along the track, it's higher at the start of the track compared to the end. So there's more ionization deposited at the start of the track than at the end. So what that means is, with the neutrons going this way and the nuclear recoils that direction, the high ionization region is closer to the readout than the tail, the low ionization region. So when it drifts, we get signals that look like this, that have this positive skewness, where there's more ionization at the start of the track compared to the end. Okay? So we do that, and then we also put the DD generator on the cathode side of the detector, where the neutrons are in the other direction, negative Z direction, and the signals then have this negative skewness. Okay? So what I do with this is, to get the directionality, I measure this skewness difference parameter, which is where I take the gem skewness distribution, and I subtract from it the cathode, the cathode side distribution. And so the reason to do this is, when you do this subtraction, any systematics that are in the measurement of the skewness, affecting the shape, the readout electronics, that's subtracted away in this difference. So if this difference is greater than 0, then that indicates that I've measured directionality within this energy bin that I'm considering. Okay. So this is, I'm not going to describe how I get those track properties, how I measure the skewness, how I measure the range of the track. I'm going to show how I do that now. So this is a signal from the preamplifier from a nuclear recoil in the detector. This is what the signal looks like, and specifically the red with all the noise. That's the raw signal that I measure, and it has a lot of high frequency noise in it. So I did a lot of work where I tried to suppress and remove a lot of this noise in software, and so I came up with. After a lot of work, I came up with these two methods here to suppress the noise, and the result. So I apply this notch filter and then the Savitsky-Gallet filter, and the result is this black curve, and this is good because it reduces the noise, but it preserves the shape of the signal. I'm not distorting the shape of the signal, which is what I want to measure. So the result is the black, and I want to point out that there's this decay tail from the preamplifier, and since I want to measure the skewness, which is I'll show how that's related to the shape, I want to remove the decay from the signal. So what I do is I convert that voltage signal into a current signal through this equation right here. And if I do that for the event that I showed on the previous slide, I get this result here. This is the current with time, and I've circled the different negative ion species. Here is the SF6 minus, and then here the SF5 minus, which I use for fiducialization. So the different track properties. Skewness, when I say skewness, that's the third central moment divided by the standard deviation cubed. So when I say skewness, that's what I mean. There are other measures of skewness. I chose that one. Also, the track length is just the extent of the SF6 minus charge distribution. That's I'll call that delta Z. And then the area under the signal, area under it, is proportional to the energy of the event. And I'll show on the next slide how I get the energies. And then fiducialization, again, the arrival time difference between the two species given by this equation, you can fiducialize. And then lastly, I calculate this ln of eta parameter, which I'll show how it's important for discrimination. But ln of eta is the peak of the current divided by the range or the delta Z of the track. Okay, and I'll show in a minute how that is important, this parameter, for discrimination. And okay, so here's that energy calibration I mentioned. So I then flip on my iron 55 source, and what this does is it emits the iron 55 emits 5.9 keV X-rays, and these X-rays interact in the detector, and they create electronic recoils. But each of these electronic recoils are 5.9 keV EE. So when I calculate the current signal and then I measure the area under those signals and make a histogram of those, I get this result here. And so the mean of that distribution corresponds to 5.9 keV EE. So I have that way I have a conversion factor from the area of the signals that I measure to energy. So that's how I get the energy for my events. And then now, right into the experiments that I did. The first one was this Cobalt-60 experiment, where I flooded the detector with gamma rays. This Cobalt-60 source is the source of gamma rays. So these gammas interact in the detector, and they create electronic recoils. And so this is the ln of eta, that eta parameter I mentioned, versus energy. And so the way the ln of eta works is that these electronic recoils, I said, they have the energy loss along the track is lower at the same energy for electrons than nuclear recoils. So that means that the peak current for ln of eta, the peak current divided by the width of the track, the widths are longer for electronic recoils. So that means that they lie at lower ln of eta than nuclear recoils, and that's the red events here are these the electronic recoil band here, and then these black events are the RPR backgrounds from radioactive decays in the detector, and as I mentioned, they reside in the nuclear recoil band. So what I do is I define this blue dashed line here to define the separation between the electronic recoil band and then define the nuclear recoil band. And then, so here's the same thing, same events, but plotted in range versus energy. You see the electronic and a couple RPR events there. And so with this, I then use the DD generator to give me neutrons. Okay, so I'm going to show some results now with the DD generator, and what I'll do is I'll describe several cuts that I apply to the data to remove junky events from the analysis, so I can get the best directionality and discrimination measurement.